Join us as we tackle coding challenges on Code Crusaders. In this video, we'll be diving deep into the problem by addressing 5 crucial elements: the problem definition, our approach to the code, an example to illustrate the code, the intuition behind the code, and the complexity analysis. The problem is non-decreasing subsequences. The problem statement is to find all the different possible non-decreasing subsequences of a given array with at least 2 elements. A non-decreasing subsequence is a sequence of elements in an array in which the elements are in increasing order. For example, given an array 4, 6, 7, 7, some of the possible non-decreasing subsequences with at least 2 elements include 4, 6, 4, 6, 7, 4, 7, and 6, 7. The goal is to generate all the different possible non-decreasing subsequences of the given array and return them in any order. Here is an overview of the approach used in this solution. Define a vector result to store all the different subsequences that are generated. Define a vector temp to store the current subsequence being generated. Define a set hash values to store unique hash values of the subsequences. Define a backtracking function that takes the current index and a hash value as input. Within the function, check if the current subsequence has at least 2 elements. If it does, add it to the result vector. Use a loop to iterate through the elements of the array starting from the current index. For each element, check if it is greater than or equal to the last element in the current subsequence. If it is, add it to the current subsequence and call the backtracking function recursively with the updated subsequence and the next index. After the recursive call, remove the last element from the current subsequence. Finally, return the result vector containing all the different non-decreasing subsequences. It uses the backtracking algorithm where it starts with an empty subsequence, and in each iteration, the algorithm can either pick or ignore the current element in the sequence and recursively call the same function for the remaining elements. To avoid the duplicate sequences, it uses #set to store the unique subsequences. Here is a step-by-step explanation of the solution using the example. Step 1. Initialize the result vector result and the current subsequence vector temp to be empty. Step 2. Define the backtracking function that takes the current index and the hash value of the current subsequence as input. Step 3. Within the function, check if the current subsequence has at least 2 elements. If it does, add it to the result vector. Step 4. Use a loop to iterate through the elements of the array starting from the current index. Step 5. For each element, check if it is greater than or equal to the last element in the current subsequence. If it is, add it to the current subsequence and call the backtracking function recursively with the updated subsequence and the next index. Step 6. After the recursive call, remove the last element from the current subsequence. Step 7. When all elements have been considered and the function has returned, the result vector will contain all the different non-decreasing subsequences of the given array. Step 8. Return the result vector. For example, input, nums equals 4, 6, 7, 7. Initialize the result and temp as empty. Start the backtracking function, set the current index to 0 and the hash value as 0. Check if temp has at least 2 element, as it is empty, it doesn't, so move on to next step. Use a loop to iterate through the elements of the array starting from the current index, 0th index, which is 4. As the temp is empty and 4 is the first element, it is added to the temp. The backtracking function is called recursively with the updated temp @4, and current index 1. Check if temp has at least 2 elements, which it does now, so it gets added to the result vector. The next element, 6, is greater than the last element in temp, 4, so it is added to the temp and the function is recursively called again with updated temp @4, 6, and index 2. This process continues with elements 7 and 7 being added to the temp and the function being recursively called. When the function returns, the temp is reset to 4, and the next element, 7, is checked. Since it is greater than or equal to the last element in temp, 4, it is added to the temp and the function is called again. This process continues until all elements have been considered. The result vector will contain 4, 6, 4, 6, 7, 4, 6, 7, 7, 4, 7, 4, 7, 7, 6, 7, 6, 7, 7, 7, 7. The intuition behind this solution is to use the backtracking algorithm to generate all possible subsequences of the given array, and then check each one to see if it is non-decreasing. Backtracking is an algorithmic paradigm that builds a solution incrementally, one piece at a time, and if it fails to find a solution, it backtracks to the previous step and tries again. This approach is well suited for solving problems that involve searching for all possible solutions. In this case, the backtracking algorithm starts with an empty subsequence, and in each iteration, it has two options: either include the current element in the current subsequence or not. The algorithm then recursively calls itself with the updated subsequence and the next index to consider. The check for non-decreasing is done by comparing the current element with the last element in the current subsequence. If the current element is greater than or equal to the last element, we include it in the current subsequence and move on to the next element. If the current element is less than the last element, we discard it and move on to the next element. To avoid the duplicate sequences, it uses #set to store the unique subsequences. As we know, #set stores only unique elements, so it can be used here to avoid the duplicate sequences. In summary, the backtracking algorithm is used to generate all possible subsequences of the given array, and the check for non-decreasing is used to filter out the invalid ones. In terms of time and space complexity, the solution has a time complexity of big O2 to the power of n into n and space complexity of big O, and the time complexity of big O2 to the power of n into n is due to the fact that for each element in the array, we have two options: either include it in the current subsequence or not. Therefore, the total number of possible subsequences is 2 to the power of n. The n factor comes from the fact that for each subsequence, we are iterating through the array and checking if the current element is greater than or equal to the last element in the current subsequence. The space complexity of big O(n) is due to the fact that we are using a vector temp to store the current subsequence and a vector result to store all the different subsequences that are generated. The size of these vectors is directly proportional to the size of the input array, which is n. Thanks for following along. I appreciate your attention, and I hope you found this explanation helpful. If you found this video helpful, make sure to hit the like button, leave a comment, and subscribe for more content like this.